Okay, so maybe we start. Okay, thank you.
All right. All right. My name is Brennan Steinbauer, and today I'll be going over my project on the COVID-19 vaccination concerns. So the objective was to predict kind of who was concerned by the COVID-19 vaccine. So I looked at various American demographics. And I guess who this would pertain to would be anyone trying to get the message across about the vaccines, like hospitals or the government. And maybe they could adjust their messages to kind of obtain more viewership. And that'll also help them as a company as well as get their message across to more people. So the data that I collected was given to the CDC when the Assistant Secretary for Planning and Evaluation did a survey. And this survey, it kind of polled and collected the data recently in April of 21. And then my data only had about, after NA omissions, just under 3,000 observations, and I had 13 variables to work with. So to start, my response variable, and a big part of the project is that it's ordinal, so it's ordered and categorical, and it's the concerns about them rolling out the vaccine. And it was ordered as follows: very low from this range, low, moderate, all the way up to very high. And so when they did survey people, they kind of were given a number, and that number, if it fell within a range, pertained to that category. So then some of the predictors I ended up going with and using was types of hesitancy. So hesitant or unsure, or strongly hesitant. And a few of the responses that would put you in that category would be like probably not, definitely not, unsure. And those are basically percentages of the county, because they did do this by county and by state. Those two variables were not used. And then also another numeric variable used was percent of the adults that were vaccinated against COVID in that county. And then also the ethnicity of the percentages of those and various ethnicities within that county. So another predictor was your social vulnerability index. So that was ranking of a number between 0 and 1. So of that county, it was also a predictor and ordinal, who's the most vulnerable. High, if you're given the number 0, it'd be lowest vulnerability, up to 1, which is very high. And that's another ranked categorical variable that I ended up using. So to start with my project, I took all my variables, paired them up, and then I ordered the response variable, which was the concern about the vaccine, and then also that predictor variable, which is your social vulnerability index. Then I wanted to look for multi-collinearity, because I figured if you're hesitant and unsure, kind of sounds very similar. So we'll see how those are all correlated. So to start, you can kind of see with the various colors, there are the different types of concern, and the colors, and the key is at the top. So high would be blue, so high concerns are blue, and then to the very end, very low would be red. And what you can notice right away is hesitant. All the hesitants are very strongly correlated. And that was a big takeaway from pairing up the data here. And then I did split up the pair plots just to make it easier to view. So the next one, I have concern against the various ethnicities. And a big one is, you can see more so with the white ethnicity, it is strongly correlated, like negatively correlated with Black, or even Asian, more strongly with Alaskan Native American, which is ALNA, and as well as with Hispanic. So you can see some strong correlation already there. And then for the last bit of data, can't really tell too much about the percent of the county that's vaccinated, or their category of their social vulnerability. And then I did have state on there initially before it was removed. So you can't really tell too much from this. And then the kind of deep dive into plotting the percent of the county that's white versus percent of the county that's Black, you can see it's very strongly correlated and negative. And so that helped lead to removing various variables in my model. and then kind of doing some plots for the hesitancies against the concern, the response variable. It does, they all are very similar, and it makes sense that the higher the percentage of hesitancy, the higher average you'd see for a higher concern. And you can see that in all the different types of hesitancy. So they are strongly correlated as well. And then looking at ethnicities, some of the ethnicities that had a very small data, very small percentages of the county, which was like Alaskan or Native American or Pacific Islander, you can't really make out much comparing that with the high concerns. But then look towards more with the Black population, which is the flip of the white percentages. As the percentage of Black increases, you can see that the average concern for very high concern goes up, and the flip is with white. And then can't really tell much with the Hispanic, other than there are a lot of potential outliers as well, which that will be addressed. And then just looking at the percent vaccinated, kind of makes sense that as the percent of the county that's vaccinated is higher, it'll probably have a lower concern than a very high concern about the vaccine. And then so plotting the correlation of these variables, it does make sense how the hesitancies are all very strongly correlated positively. And then you can see white ethnicities very strongly negatively correlated with Black as well as Hispanic, and slightly strong with the other ethnicities as well. And so this was kept in mind as I made an initial model. So to start with the initial model, I used the POLR, which is a type of logistic regression that takes into account the ordered categorical variable, which in our case was concern. And to kind of stay away from multi-collinearity, I broke the model down after, so this is my initial model, and you can kind of see I have a few, white is very strongly correlated. And so I removed that, the white variable to start, to kind of see how the rest of the correlations shook out. And the AIC is just under 7,000. So the AIC kind of went up a little bit, dropping a few variables, but I did drop the white variable, and kept all but Pacific Islander as well for ethnicities, kept all the hesitancies, which that surprised me mostly, because those were the strongest correlated, but they didn't appear in the multi-collinearity of this ordered logistic regression model. And then I decided to keep Black because that was the inverse of the white variable. And the VIF is small, but it's not like 2000, which white was. So I decided to keep that to kind of see how that response would affect the modeling. And to kind of start with all the data with this set of variables, my precision, which was the correct predictions over all of them, was just under 50%. And so into the methodologies and the various ways I wanted to model this data, I used the ordinal logistic regression, which is the POLR, LDA, QDA, and then I try to do some neural networking as well. So when I split up the test, the train, which was 25 and 75%. And then when I did my first training model, which the summary is on the right here, you can already tell that the AIC went down significantly to now just over 5,000 instead of just under 7,000. And then most of the variables, you can see they're fairly significant. And when it's predicting the concern, I want to see how that affects when I put this model to test data. So when I have my test data, so I used training data, built the model, and then I fitted that with the test data to see how it worked. The precision initially went up to 55.55, so it did improve. And the same variables I have listed above, so those weren't changed, but still wasn't that great of precision. So then I implemented 5-fold cross-validation, and the average is 45%. which isn't that great. And then I have the actual predictions listed on the left here. So you'd expect 172 of the test observations to be very low, but the model only predicted 103. But right next to it was low. So if you include very low and low, 144 is pretty decent, but it's not as precise as I'd like it to be. So I wanted to implement a different type of model, see if it would improve on that. So in came LDA. So it was the same model was kept as a ordinal logistic regression model. And I plotted that, except this doesn't take into account the ordered response variable, or the order predictor variable, SVI. But looking at the model, precision's fairly similar, about 10% lower, but the average from the 5-fold cross-validation is pretty much the same. So it didn't really improve anything, unfortunately, but it's not that different than ordinal logistic regression, which that surprised me most. So then I tried to implement the QDA, same model, except SVI category was dropped, as that did improve the model, but as you can tell with the precision, it's still low, fairly similar, and slightly lower than the last two. And it kind of went down. So very low was predicted better, but as you can see, as you go down to very high, the prediction is getting worse and worse, unfortunately. So then my last attempt was to do neural network. And so with neural network, it was a new topic we discussed last time in lecture. And when I was running the code, you're not having a categorical response. You have a categorical response variable, but not a predictor variable. So the only difference between this model and a few of the previous ones is SVI was removed. So the model is fairly similar to QDA in the same types of variables I'm predicting concern. And it also doesn't take into account the order of concern. And when I did run the neural networking, it was behaved the worst. I did cycle through various types of the hidden nodes in the model, and it does take a lot of time, and the code usually doesn't work. It doesn't converge half the time. So I ended up working on a 1-2 for the hidden nodes. And then when I fit it with the training class, this is the training results, it's still very low, not precise at all, 15%. And then when I take this, so I have the training model, I fit it, and then you can kind of see where I ended up mutating some of these, that was the term for the code. You would mutate the variables that had a lot of outliers. So going from left to right, the data kind of condensed it when you mutated it to try and improve your modeling. And then when I did this and fit the training model on the test data, this is the initial model still, error of 717. You can kind of see the nodes I implemented. And so high error, very high error, not all that good. Looks very messy. But when it was all said and done and fit on this test data, precision was about the same. It went down 1%, and it, which would make sense if it wasn't good with the training data. Wouldn't make sense to fit the test data any better. And doing 5-fold cross-validation with the neural network, taking the average of running this code 5 times, which an issue with this is if you have a select, so it is random. So if you have a random set of code that you're running the neural networking on, and it doesn't converge, it crashes the whole thing. So it took a lot of attempts to make sure that I could even run it 5 times, and the average was still fairly low for precision. And then to kind of get a summary of all these models, I implemented a Cohen's kappa. And so in a paper written by McHugh, it kind of tests your inner rater reliability, and it's how we can interpret this. So when someone collects the data, you kind of want to compare that to another rater and what they collected and see how similar, and if they were off, because there's 2 types, a weighted and unweighted. The weighted incorporates the off diagonal terms. So let's say they're close in the very low prediction, but one was had a lot of very highs, which is very far off. But if they both had a few in the very low and low, it'd do less of a penalty. Or you can have the unweighted where it just takes the diagonal terms. And these are kind of the values that you'd see for your weighted kappa if there's reliability between the two raters. And you'd hope for anything above moderate to almost perfect with these results. And
okay, so wrap up presentation.
What?
Wrap up your presentation.
Oh, sure.
Yep.
So then in summary, the Cohen's kappa kind of went along well with the ordinal, LDA, QDA, and neural network results, being that the ordinal and the LDA had the best results, the most precise, just under 50%, and their weighted kappas were higher, so they're moderately significant. And then all the way at the end, the neural networking was less than 0, meaning that comparing the actual to the predicted from the test, it was very far off, and neural networking did very poorly, but ordinal or LDA were pretty much the same in predicting vaccination concerns. And then I'd probably extend my research into Cohen's kappa further and kind of get a sense for weighted or unweighted more, work on machine learning with a higher capacity laptop, maybe just do binary results, and then I'd probably add more variables like age. I'd say age is a big factor in modeling your vaccination concerns. And these are my sources. Thank you.
Okay, thank you. So yeah, I think it's good that you compared many models with cross-validation and the validation approach. Yeah, so you can see that the neural network is really hard to apply. So theoretically, probably it's better to classify everything, but it's hard. Maybe the number of nodes, maybe still there is a room to optimize, but in reality, it's really hard to optimize all hyperparameters.
Yeah, it's very. Thank you. Any questions?
We can understand why it wasn't popular in the 1980s, maybe 1990s and 2000s.
Oh, yeah, I'm sure it took them a lot longer to run it.
Yeah. Mm-hmm. Yeah. Okay. So, do you have any of you has question for Brennan's presentation?
Yeah, so real quick, so was the data readily available like this? I know you said you did some, made the response variable like ordinal, all that stuff, but.
So all I had to do was just run a quick line of code that like you set the levels for your, so I set the levels as very low, all the way to very high. Other than that, naming. So like a lot of these variables, it was like percent hesitancy, just very long. So the only thing that took a long time was just to rename every variable to something I could type up easily. Other than that, it was very accessible.
Nifty, cool. I guess a little unsurprising that they're taking those statistics, but cool.
Right.
Yep. Okay, so maybe we go to the next presentation. The Sai, can you share the screen?
Can you see my screen?
Yes.
Good evening, everyone. I did my project using the bike sharing data set. The bike sharing data set is from the UCI machine learning repository, and it was collected during 2011 and 2012 from the Capital Bike Share System in Washington, DC. It includes 14 variables, and it includes information such as weather conditions like temperature, humidity, airspeed. It also includes details of the time of the day, like the year, the month, whether it's a working day or a weekend. And the response variable is the count of total rental bikes. So basically, I'm trying to predict how many bikes are rented during a particular time of the day using weather conditions also. And there are about 17,000 observations with no missing values. So this is the structure of the data. The first variable is the date. The second variable is a season, which has 4 levels, with 1 being spring, 2 is summer, 3 is fall, and 4 is winter. Year is 2 levels, and 0 being it's from 2011, and 1 being it's from 2012. Month has 12 levels, each indicating the month, and the hour variable has 24 levels, each indicating the hour. The holiday variable includes 2 levels, with 0 being it's not a holiday and 1 is a holiday. And weekday includes 7 levels, each indicating the week, the day of the week. Like for 0, it's Sunday, with 6 being Saturday. And working day includes 2 levels, with 0 and 1. 0 being it's a weekend or a holiday, but 1 being it's a working day. And weather situation has 4 levels, describing the situation of the weather. So with 1 being that it's clear outside, sunny, and 2 being it's like a bit cloudy, and 3 it's like light rain, and 4 it's heavy storm and snow. And temperature is collected in Celsius, but then the data set normalized the temperature to be between 0 and 1. And the same thing happens with atmospheric temperature and humidity and wind speed. And the last variable is my response variable, which I'm trying to predict. So for cleaning the data, I removed the first variable, date, because information such as year and month are already there. So I thought that the first variable is redundant. And I also removed atmospheric temperature because when I tried to find the correlation between the temperature and atmospheric temperature, it was really high. So I chose to remove it in building my models. So some descriptive statistics. So in total, the number of rented bikes as a year increased from 2011 to 2012. And here is a time series graph with the y-axis showing the total count of rental bikes, and the x-axis the month. So the dashed lines indicates the start of the new year. So on the left, we can see that it starts from January 2011, ending with December 2012 on the right. And we can see that the total number of rental bikes increased in 2012 compared to 2011, as seen in the bar graph before. And we can also see some seasonality, like during the winter months, like January and February, it's winter, so it's the number of rented bikes is less compared to summer months like in June, July, and August. And the same pattern applies to 2012, like in January and February, there are less bike rentals compared to the summer months. This is also another bar graph. So on the left, we can see the correlation between like weather situation and the number of bike rentals. So during the weather where there's clear sky, there are more bike rentals compared to days when there's heavy rain or snow. And on the right, we have the bar graph with seasons. So bike rentals in the fall and the summer are higher compared to spring and winter. Most likely it's because the temperature is higher during the summer, and it's nice to go outside and ride and stuff. And this is another time series graph with the y-axis, the days, and the blue dash line indicating the start of the new year. So the graph on the left indicates information from 2011, and the graph on the right of the dashed line indicates information from 2012. And the left y-axis includes the total count, the total number of bike rentals, and the right y-axis includes the temperature in Celsius, which is normalized from 0 to be between 0 and 1. And we can see that like when the temperatures are high, there are more bike rentals, and when the temperatures are low, like around here, there are low bike rentals. And it's also like we can see that month is also a factor here, because January and February there are low temperatures and thus low bike rentals. And this is a correlation plot. As seen before, this is the last variable is the count, the bike rentals, number of bike rentals, and we can see that it's correlated with the temperature and the month and the year. and the season as well, and the hour of the day. So as it becomes from morning to noon, it becomes warmer. So probably there are more bike rentals in the afternoon because it's warmer. And so for building models, so since this is a time series data set, I didn't randomly split the data. So instead I used the first 80%, which is the first about 14,000 observation to be in the training set. And I used the last about 4,000 observations to be in my test set. So the first model I built is the multiple linear regression. And we can see that almost most of the variables are statistically significant. And we can see the coefficients like temperature, month, and year are positive, just like as we have seen in the bar graphs and the time series graphs. The good thing is that there's no multicollinearity. All the numbers were below 5, but the error terms were correlated. So the error term of a particular hour was correlated with the error term of the previous hour with a correlation coefficient of 0.723. And also when I tried to plot the residuals over time graph, I found that as we move towards 2012, the variance increases. So as time increases, the variance increases. So the correlation between the error terms and the constant variance is violating the IID assumption of the multiple linear regression. So the correlation between the error terms is underestimating the standard errors. So I then built the generalized least square model, which accounts for the correlation between the error terms. So we can see that now the standard errors are much higher over here, and not all the variables are statistically significant, like season or month or the weekday or the working day. So I think this is a better model than multiple linear regression. I also built a KNN model by finding the optimal value of K using the test MSE. And I found out that the optimal K is 5. I also built the random forest using this argument to be 6. So each a tree in the random forest only uses 6 variables, not all the variables. And the number of trees is 500 with the mean squared residuals to be 1,468. I also built a generalized additive model of the GAM. And I found we can see that all the variables are statistically significant, just like the multiple linear regression. And I also used natural spline to estimate the temperature, the humidity, and wind speed with degrees of freedom 2. Like when I try to plot the scatter plots using the pair function, I found that temperature and like the number of bike rentals had like a parabolic thing, so shape. So I tried to use 2 as my degrees of freedom. So summarizing results, so I used all my results to predict the values for using the test data set, and this is my test MSE, and all the test MSEs are high for every model, but then the lowest is the random forest with only 7,832. So the winner of all the models is the random forest. So in conclusion, random forest seems to better predict models compared to other models. And previously I used the generalized least square, which only accounted for the correlation of error terms. But then in the future, I would like to use the Koch or the weighted least square to also account for the non-constant variance of the error terms, because the multiple linear regression, the non-constant variance violates the IID assumption. So in the future, I would like to use Koch and weighted least square. Thank you.
Okay, thank you, Sai. So, so the data set is time series data. So
Yes.
it's a little harder to deal with because anyway, so these are not IID. And there are basically two techniques to deal with the data. One is to use the models, the common to the data science, and another is the time series analysis that may correlate the observations with the recent past observations. So that hasn't been covered in this class, but in such a case, the randomized validation is even harder. So we split the first several months as training, and the last few years for the test set is good. And basically, the data analyzes the two things. The one is the seasonality, and the other is the effects from other variables such as temperature. So the seasonality, often time series data has already removed the seasonality. So if you see some time series data on the website, for example, the Fred website, it's already removed. So in the future, anyone who wants to do time series analysis, you have to be careful whether that is already seasonally adjusted or not adjusted. Yeah, I think you compared many methods, and it's very useful, the conclusion. And the only one thing I think it could be improved is that the months and hours should be factor variables, because we don't have any reason to believe that the relationship is linear. So
yeah, they are factor variables.
Oh, factor variables, but the DF is 1 in your presentation, right? Degrees of freedom for hour means the 0 to 23 or something, right?
Yeah, I don't know. When I tried to, I did change them to factor. I don't know why the degrees of freedom is 1.
Yeah, I think somewhat it wasn't successful, right? Probably, yeah. So yeah, but I think you covered many methods. Does anyone have any question to Sai? Anyone who are doing the time series analysis? Probably no. Usually I don't recommend the time series data because it's harder to deal with, but yeah, certainly it makes some sense to in your result. Okay, so maybe we go to the next one. Sorry, I misspelled your name, but Mariam?
It's Mariam.
Mariam, sorry, yeah, Mariam. Yeah, you can share the screen.
Yeah. You can see my screen, right?
Yes.
Okay. Give me 1 second.
Yeah, you can. Yeah.
Okay.
Yeah, you can start. Yep.
Right. Hi, everybody. So my project was on cardiovascular disease prediction. So without further notice, I'm going to move to the summary. So I did an introduction. I gave a brief introduction and then did the data analysis, show the methodologies that I use, summarize my result, and then gave a brief conclusion too. So introduction, cardiovascular disease is a major health problem, the leading problem of death actually in this century. An attainable and accurate prediction of heart-related diseases is therefore needed. So in this project, I used 3 different models to predict cardiovascular diseases. So logistic regression, KNN, and random forest. My goal was to use those algorithms to implement and compare the accuracy in this exploratory data analysis and to get more information on which kind of attributes may cause incoming heart disease. So data analysis. The data that I use in this project can be found at the UCI Machine Learning Repository. The data includes 303 observations and 14 variables. The target variable was considered as the dependent variable. Actually, I wanted to give a glimpse of the data set, but I forgot to, I'm sorry. But the 14 variables are the age, sex, CP, which is the chest pain experience, stress, BPS, which is the resting blood pressure, call, serum cholesterol, FBS, fasting blood sugar, resting G, resting electrocardiographic measurement, Thalach, which is the maximum heart rate achieved. Exang, exercise induced angina. Old peak, the slope of the peak exercise, that segment. Slope, the slope of the peak exercise segment. CA, number of major vessels. And TAL, which is a blood disorder called thalassemia. And then the target variable, which is actually to predict if the person has the heart disease, yes or no. So 7 of those variables are continuous and the other 7 are categorical. And my data was displayed as a CVS Excel file. So I did a data pre-processing to see if I would need to modify anything before moving to the analysis. So this is the code that I run to see if there was any missing value. And as we can see, we didn't have anything missing. I also did the code with the column test to see if there was anything missing, and nothing was actually missing. So here I presented the outliers with box plots. So as we can see on the data TRESS BPS, cholesterol, and Thalach, we see some outliers from those box plots. Everything just to see if I would need to modify the data, which I actually did before moving to the methodology. So let's visualize the data. Here we have the distribution of people by heart disease. So the value count actually show that 165 people have it and 138 do not. I wanted to show the confusion matrix. Just the table to show the value counts. So the distribution of categorical variables. So the sex, the, chest pain type, fasting blood sugar, and resting electrocardiographic results. All of those are categorical variables, and their distribution were actually summarized in those bar plots, those bar graphs. The rest of it, exercise-induced angina, exercise peak, and thallium stress tests are also in summarized in those bar graphs. So we were just trying to visualize the data here. Here I tried to give a correlation map. So just to see if the variables are correlated and how they are actually correlated. So the darkest colors represent the highly correlated one, and the lightest one, the least correlated variables. For example, we see that CP and target are actually highly correlated with a coefficient of 0.43. And in the contrary, let's say all peak and slope have a negative correlation coefficient, which is negative 0.58. So they are not that correlated. So let's move to the algorithm implementation. First, I wanted to say that the data set was separated into training and testing set for this evaluation process. So the 80-20 method. The first one that we did was the logistic regression. And here is the summary of what I got. As we can see, so here we have the estimated coefficient, the p-values and stuff. The estimated coefficient, so yeah, and the p-values. So we can see that a lot of coefficients are actually not that significant because their p-value is actually higher than 0.05. But on the next slide, I'm gonna tell you what I did with those. Oops, sorry. I'll have to go back, sorry. Right, so on the next slide, I show that a lot of variables are actually not significant. Rest CG, for example, FBS, slope, and exang. So I removed them by the backward method. And here was my final result. So the p-value, we can see now that the p-values that are here are all significant because they're all less than or equal to 0.05. So that was my final result for the logistic regression. The second one that I did was the K and N. So on this slide, I didn't have much space to show you what was actually going on, but I did a tenfold KNN, like repeated 10 times. And the results obtained were actually summarized in those two graphs. So here, yeah, so a KNN with 10 repeated tenfold cross-validation. And yeah, two sample splits were done. So the first one was the red one and the second one, the blue one. And the ROC curve that I obtained is right there. And it was done with a K equal to 5. So the result is right there on the right side. The third method was the random forest. So on the right side, we can see what we've had, what we've had when we run it. So we obtained a sensitivity value of 90.6%, which showed that 90.6% of the patient with heart disease were correctly classified. Also, the specificity value was equal to 82.7%, which means that 82.7% of patients without heart disease were correctly classified. So from that experiment, we get that random forest correctly predicts 29 classes of patients with heart disease and 25 classes of patients without heart disease. So
sorry, is this for the test set? Sorry.
The test set, yes.
Okay, sure. Okay.
So the true positive is 29 then. The true negative 25, sorry. False positive 4 and false negative 3. So this is what we've obtained from the random forest test. And I also did an ROC, the raw curve for the random forest, and we've had an AUC equal to 0.93, which was actually really high to me. So it just indicates that the model accurately predicts by 93% whether the patient suffered from heart disease or not. So when we did the work, like in the proposed work, we had a classification accuracy of 83.6% for prediction of heart disease by using this algorithm. I will show it in my summary. Right, so in this summary, we've compared the 3 models that we've used. So by looking at the bar graph, we can see that the linear regression is actually the more accurate model. It predicted what we wanted to know with the highest accuracy. So with a coefficient of 0.88, so 88.5%, right? The KNN coefficient was 0.68 and the random forest was 0.83%. The ROC curve, this is kind of a repetition because I've shown it in the previous slides. So the area under the curve is 0.93, which was high. So it just quantifies the model classification accuracy. So conclusion, from our research, logistic regression was actually the most accurate to predict the risk of having a heart disease. The following attributes are selected after the backward elimination process, considering the values of P, which were actually lower than 5%. The value under the AUC curve that was obtained is 93%, which was satisfactory. I think that the model could actually be improved by using more data and techniques. And also, I think that we needed more attributes and many more observations to analyze data with high accuracy. For example, the data that maybe the data could have included social daily life, physical attributes, whether the person is smoking or not, drinking alcohol or not, exercising, and those kind of stuff. So that was it. That was my presentation. If you have any questions, I would be glad to answer them. Thank you.
Okay, thank you, Mariam. Can you go back to the KNN slide?
Sure. Hold on.
Yeah, I think it's good that you compared many methods, but especially when, yeah, I think the one slide before, sorry, slide 13, yeah. So you tried several different case and you choose somewhat optimal one.
It was a tenfold cross-validation. So the first one, so I did a first sample data split. Like the
I
data I split it first, the first sample was on the left right here. This is what I got. And then the second split is on the right side.
So K means the number of
Of
K in K
K
nearest
is equal to
neighborhood.
10, yeah.
K is K nearest neighborhood, you mean?
Right, yeah.
Okay, I see. Then left-hand side is the training.
And right-hand side, that's yes.
Is the test. Okay, yeah,
Right.
yeah, that's convincing.
I'm sorry
So,
that I didn't
yeah,
specify it like that.
Yeah, I'm fine. It's just
Yeah, I just called it like first
Yeah.
data split and second data split. So
yeah, I think it's convincing. So if you haven't optimized K, then of course K and N is inferior to others. But you optimized K, still some other methods work better. So yeah, that's a good reason.
Oh yeah, that's why I had a
that's
why I had a K and value of like I think that was
yeah.
Why it was not that accurate because I have 0.68.
Yeah. So probably
Right.
for this modeling, maybe logistic or random forests are better. Yeah, I think that's great. Yeah, that's great results. Okay, thank you. So
Thank you.
Does anyone has any question to Mariam? Many of you have done the binary classification, so no questions, or maybe at least someone can ask a question. Any questions from maybe some graduate students? No. Okay, so maybe we go to the next one. Sarah, can you share your screen? Or maybe I. Okay, I see. Yep, you can start. I cannot hear you. Maybe turn on the mic.
Can you hear me now?
Yes.
Okay, sorry.
Okay.
So my name is Sarah. When I was preparing for this presentation, I looked through a couple of different data sets. Ultimately, I ended up going on one that had a few factors, including wine quality. Mostly I picked it just because I like wine myself, but I don't really know a lot about it. So I was hoping to figure out if there was a way to determine the quality of wine based on a few different variables. So my data description, I use the wine quality data sets available at the UCI machine learning repository. I use two different data sets, one on red wine, which contained 12 variables for 1,599 different red wines, and then one on white wine quality had the same 12 variables, but for 4,898 different white wines. So they each had the same variables, which were fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, alcohol, and then the overall quality. So my objective in this was to use logistic regression to determine which of the first 11 variables are statistically significant to the overall quality of white and red wines. Once determining the significant variables, I determined what type of relationship each had on the quality from the odds ratio. I didn't have to modify the data too much. It was pretty easily accessible. However, I did separate them. When I put it in Excel, it was all in one column. So I just used an Excel function to separate it so it was easier to read and then easier to work with in R. Once I got it in R, I only kept the first 1,500 samples. That way it was easier, so there was a nice even number between the two since the white wines had a lot more. There wasn't any NAs or anything in there, so I didn't have to work around that at all. The quality variable was a scale of 3 to 8, so just to make it a little bit easier to work with, I separated two different classifications. I used 0 for a low quality wine, which was a rating of 3, 4, or 5, and then 1 to represent high quality wine, which is a 6, 7, or 8. My method for this was applying logistic regression to the data to determine which variables were statistically significant. Once determining the significant variables, I use the exponent function within R to determine the odds ratio of each significant variable. So I did the white wines first. I've got my R output on the right there. I took p-value less than 0.05 is significant, which gave fixed acidity, volatile acidity, residual sugars, density, pH, and sulfates as significant for white wines. And then again, I've got my output on the left there to read through it. Basically, for every 1 unit increase in those different variables, the odds of the wine being of low quality increased by those factors. So fixed acidity, for example, was 1.4. And then for red wine, again, I took p-value less than 0.05, which gave volatile acidity, citric acid, chlorides, free sulfur dioxide, total sulfur dioxide, sulfates, and alcohol. I did think personally it was interesting that it was different. I mean, obviously red wines and white wines taste different. I just kind of thought it was interesting to see how the different significant factors for each one were. So again, for every 1 unit increase in those different factors, the odds of it being low quality increased by the factors to the right. The volatile acidity, for example, was 2.85 e to the -2, so pretty small. So my conclusion on these was that for white wines, obviously there were significant variables, but none of them had a huge effect. I had a plot showing this in here, but I don't think I saved it before presenting. But essentially it just showed that there wasn't really a linear relationship. There was like a few outliers which stood out, but for the most part, it was pretty evenly split, even though the factor would have the same number, like for pH example, have the same pH level. But there was both high quality and low quality wines. So when shopping for white wines, you could try to watch for those variables. However, for something, I don't think any of them had a large effect, where if you found one that didn't quite sit well, like it was supposed to have low pH and it had high, I don't think it would necessarily ruin the quality of the wine. And then for the red wines, again, they were statistically significant variables, but none had a large impact. So same thing, you could look for those. But in my personal opinion, I don't think one factor would affect the overall quality too much. So overall, due to the fact that none of these variables had a large impact on the quality of a wine, I would say that it's actually a combination of the variables that determines it. It could also be affected by a variable that I didn't have, and I got this data set online. I didn't do it myself. I'm not a wine expert, so I don't know what other factors would affect it. But I think in doing a little more research, I could find other variables to look into. Given more time, I think it would be interesting to look into how different combinations, looking at like 2 or 3 specific combinations of each one, would affect the wine. And that is all I have on mine.
Yeah, thank you, Sarah. Yeah, so this data set is pretty popular data set, and many students, especially in 5030, analyzed this data. And the difficulty is how to use the response variable. So usually the response is, the rating of the wine, and it has 6 levels, right? So 3 to 8. So one way maybe to use the ordinal model, what Brennan used, maybe multinomial models LDA that can be used, or dichotomize the result to logistic regression. So only 6 levels. So probably, continuous model isn't really optimal. So you used logistic regression, right?
Yeah, after I did it, I noticed that it wasn't great, but at that point I was too deep into it and I didn't have time to switch it around. But yeah, I think if I was going to do it again, I'd probably go a different route with it.
Yeah, so you use logistic, right?
Logistic, yeah.
Yeah, okay, yeah. And maybe it's a little better if you, interpret the coefficients, the positive coefficients, for example, more acidity, higher rating, or something like that. So interpretation is always the more insightful to answer your questions. Okay, so do you have any question to Sarah?
Hi, so
okay,
I know you said there weren't very many significant things, but did you find any sort of consistency with your personal tastes in your results, I guess?
I thought about that actually. I didn't look into it. So I know like for my personal taste, I prefer like a light red. What I wish I would have done is had actually looked into it to see the different factors of light or red wines compared to like the darker ones. Because I refuse to drink dark red, but if it's like that kind of clear red, I do like it. So I didn't look into that, but I think I probably will just to see if I can find other ones that would kind of follow along that I would like.
Okay, cool.
Any other questions? Okay, so next, the mirror. Can you share your screen?
Yep.
Can
you see my presentation?
Yes.
Pretty cool. Hello everyone, my name is Mira Zranek, and I'll be presenting the analysis I did on the data collected from thousands of Olympic athletes dating all the way back to 1896. Originally, I was looking into data sets describing different track and field athletes from the Olympics to categorize them by their various traits for like the different events. That topic interested me because I'm a track and field coach at the high school where I ran at. I was having no luck though finding any information on that topic, so I did stumble across this data set of all of Olympic athletes for all events. The objective of this study was to compare analysis of the Olympic athletes using the linear discriminant model and the k-nearest neighbor model to determine the sport that they participated in. So first I'll be presenting some background information that I felt was important and would help describe the data set. Then I'll describe the data and the methodologies used for each observation. And finally, I'll discuss the results and conclusions I determined from this analysis. So first, some background. The Olympics began in ancient Greece in the 8th and 4th century BC. These games included running, long jump, shot put, javelin, boxing, pancration, which is similar to wrestling, and equestrian events. A man named Baron Pierre de Coubertin founded the modern day Olympic Games in 1896. The first games consisted of 280 athletes, all men, competing in 43 events from 12 different countries in Athens, Greece. The only years the Olympics did not occur were in 1916, 1940, and 1944 due to World War I and World War II. In 1994, the Winter and Summer Olympics were separated to alternate every 2 years, and now there are 51 events, 33 in the summer and 15 in the winter. Now let's discuss the data. The original data is from figshare.com and covers athletes from every Olympic Games between 1896 and 2016. This data set is comprised of 15 variables for 271,116 athletes. These variables for each athlete include information such as their name, their age, sex, weight, height, sport, year competed in, and country they represent. Due to the length of time it would take to run the analysis on all of those data points, I chose to look at only the Olympics held between 2000 and 2016, meaning there were 4 Winter and 4 Summer Olympics, and this left 5,069 athletes, which was then filtered down to 4,988 athletes after removing the NAs. Here is a table of all 51 possible sports that athletes could be categorized into of the whole data set. All the sports here should be recognizable except for athletics group, which is better known as track and field. Here's a visualization of the breakdown of athletes by each sport and sex. As you can see, athletics, swimming, and gymnastics make up the majority of the athletes recorded in the data set. Here are some pairwise comparisons of the athletes by the 4 predictors used in this analysis. I'll discuss the predictors in more detail in a minute. Each color is correlated to a different sport. As you can see, there seems to be somewhat of a trend between these graphs, but since there are 51 different sports represented, it's harder to draw any conclusions from just these graphs. So now that I've described the data, I'll go over the methodologies I used in my analysis. All models used in this experiment were done using these train and test groups. I broke them up by choosing points before 2013 for the train group and after 2013 for the test group. The year 2013 was chosen because that would leave one winter and one summer Olympics in the test group, and all the sports analyzed would be represented. As you know, linear discriminant analysis calculates and estimates the coefficient of the Gaussian density. These values will then be plugged into Bayes' theorem to obtain the probability each observation is in each class. Each observation is then classified based on the category where the probability is the highest. The total number of classes were 51, and the number of predictors were 4. Sex as a predictor had 2 possible options, male or female. The age predictor ranged from 13 to 61. Heights of each athlete ranged between 133 to 219 centimeters, and weight between 31 and 175 kilograms. I then did analysis using the k-nearest neighbor technique, which determines the observation of the testing group and chooses the closest points to the training data. An estimated probability is then determined for each value and classifies the observation based on that. The k value used for the analysis was k equals 17. The total number of classes was 51, and the number of predictors were 3. Sex as a predictor was not able to be used for this test because its limited range of just being male or female. All ranges were the same though for the other 3 predictors. After running both models, I was able to obtain the breakdown of each observation and how many were correctly categorized. So the LDA model had an overall 20.98% success rate for categorizing each observation based on the predictors. Here are the 10 sports with correct categorization. Athletics, gymnastics, and swimming had the most accurately categorized observation compared to all of the other sports. For the KNN model, correctly categorized 19.2% of the athletes for 19 of the sports. In this model, athletics, bobsled, gymnastics, and rhythmic gymnastics had the highest percentages correct. A comparison of both models shows that LDA outputs 230 correct classifications, which is more than KNN with only 212 correct. The KNN model, on the other hand, covers 9 classes more than LDA. Overall, LDA has the highest percent of correctly classified observations. After analyzing this data set, I realized that the percentage of correct classification seemed to be extremely low. Of course, this could be because anyone competing in the Olympics is in pretty good shape, and that would cross over between sports. But I wondered if there was another reason that there was such a high error rate. Looking at the incorrect classifications, I had a lot of the sports were mistakenly classified as either athletics, gymnastics, or swimming. So I wondered if categorizing each sport into a smaller number of classes would improve the percentage correct. So I categorized each sport into 7 categories: snow, ice, gymnastics, skill, water, cardio with a ball, and cardio. The snow, ice, and water categories are broken up by the environment they were performed in. Gymnastics contains all sport where I thought flexibility was a main component of the sport. Heavily skill-based sports were grouped together in the skill category. And finally, I separated all the cardio sports based on if they are played with or without a ball. I know this is very subjective and a few sports could be put in multiple categories, but for the purpose of this analysis, I chose to break them down in this way. The breakdown of athletes by each category and sex can be seen here. As you can see, cardio, water, and snow categories make up most of the observations. For the data broken into categories, the total number of classes decreased to 7, but the predictors stayed the same as the first LDA for the LDA model. For the KNN model, the total number of classes also decreased to 7, but the predictors stayed the same as the first KNN model. The LDA model of the categorized data had an overall 29.58% success rate for categorizing each observation based on the predictors. Here are the 5 categories that observations correctly classified, and the water category had the most accurately categorized observation compared to all of the rest. For the KNN model, it correctly categorized 19.4% of the athletes for all 7 categories. in this model, cardio had the highest percentage of correct classifications. So comparing both models of the categorized sports showing similar outcomes as the previous analysis, LDA outputs 326 correct classifications and KNN only has 214. The KNN model, on the other hand, also covers all of the classes where LDA only covers 5. And overall, LDA has the highest percentage of correctly classified observations. If we compare categorizing the sports into versus not categorizing them, we see that the second test improves the percent correct of classified data. The improvement was seen the most when the data was run through the LDA model, with almost 30% of the data being correctly analyzed when categorized. After running both these tests 2 different ways, I was able to make a couple conclusions. First, the LDA is the best model for this data set. Between the 2 that I tested, I outputted the highest percentage of correct classifications using this. Categorizing the observations helped improve the success of correctly classifying the data. And I think this model can be improved by optimizing the categories more, maybe looking more at which sports were initially overlapping in the original model. But due to time, I wasn't able to really dive into that. And thank you for listening to my presentation. Are there any questions? I also have my references on this page too.
Let's see. Yeah, I haven't ever used the figshare.com. So does that website have many data sets?
Yeah.
Okay. Have you ever used it before?
No, I know that they got their data from the official Olympics website as well. So
I see.
It was directly taken from that.
Yeah, it looks interesting site. Yeah, it's very good comparison, and it's very easy to follow presentation, and and it's very meaningful, right? So if you are very high and but very skinny, then what sport may be the best to play? Yeah. Maybe you can use that information for some purposes.
Yeah, I think one problem is that because they're Olympic athletes, everyone's in pretty good shape. So there's a lot of crossover between sports because there's generally a form for each.
Yeah, so grouping it makes sense. And also the first analysis, I think I'm not feeling the accuracy rate is not too low. I mean, there are many sports, and originally probably it's hard to distinguish them. Yeah. So yeah, I think pretty good result. Okay. Does anyone have a question to Mira?
Could you jump back to the condensed category results, please? I just wanted to see those.
Sure.
Or if I just ask, so for both models, it did improve?
Oh yeah, this one. Yeah, so it improved for both, but like the KNN model only like a little bit, but the LDA had the biggest change.
Gotcha. All right, thank you.
Does any other student have a question?
I guess for you, Professor.
Yep.
Because I did consider condensing the levels of concern into 2. Would there be a specific way to weight that? Like, I know when she condensed a few categories, some had more sports. Would you recommend weighting that then differently?
Sorry, what do you mean weight?
So you're predicting the sports, and one category now has 8 and another has 5. So would there be a penalty then? Because you're more likely to guess that one correctly just because.
When we group some group have 5 categories and another have 8 categories, and how to do that? I don't think any problem about that. So if original predictor is the original response is ordinal, then maybe we have to care a little bit about it. But this is entirely categorical, the non-ordinal data. So yeah, I think
The one thing I was worried
yeah.
about was this having way more observations in like these certain categories. But
maybe the possible analysis is the before the doing the supervised learning that you can do some classification as the non-supervised learning. Then you can optimize, you can group the sports in a better way. That is possible way to classify the data. So at first, maybe yeah, supervise. Yeah, maybe this question is more like the in between supervised and unsupervised learning. Then probably the question can be answered better, right? So there may be some categories, maybe gymnastics, maybe some sports are good for the maybe larger people, and some sports are good for smaller people. So maybe the those categories may not be optimally set. So maybe that can be improved if by further research, but I think the grouping different number of sports don't have any problem, I think. Does anyone else has any question? Okay, so that's great. I think that today we had very unique and good presentations. And next time we have the 6 presentations. So probably we will need a little more time, maybe possibly up to 7:30. So Shuraya and Nicholas and Connor, Arif and Robert and Shiv. So they prepare for the presentation. And the presentation is on 28th. So next Thursday from 5:30 p.m. And just the comment on each of the presentations in Canvas. So each comment counts as the 1 point for your quiz credit. Okay, and thank you, the Brennan and the Mariam and the Sai, Sarah and Mira. And hopefully that we will see more interesting presentations on April 28th. Okay, do you have any questions? Okay, so see you next Thursday.
Thank you. Have a good night.